We got started talking about angular measures yesterday and radians and that type of thing. So we'll continue on, and let's mention first of all radians. And I've been instructed to tell you Feliz Navidad. Our assistant in here is Spanish, and she's trying to teach me Spanish, not being very successful. And she thought I needed to tell you Merry Christmas in Spanish. So now, I've done that. Will you leave me alone now? She says yes. All right. We give her a hard time, but that's all right. She deserves it. So, all right, let's talk about the radian here then. I wish I had the camera set up on her so you could see her now, but you can't do that. All right, there are 2 pi radians in a complete circle. I think we went over that yesterday. The angle theta is the angular position of the position vector from a reference angle, or the reference direction is analogous to the linear position. A lot of words that are very simple in their explanation. If we have a circle, we start with our reference position in the center. We've got an object on the outside. We draw a position vector to that point, and that position vector is called the radius. We have a arbitrary reference system that we put, and that's supposed to be right in the center there. I kind of missed it. But we have this arbitrary reference position that we call 0. This angle right here is called theta. And so that's the angle from our arbitrary reference position, which is the x-axis in this case, and the radius. So that's what that says. The angle theta is the angular position of the position vector from a reference axis. So here's our reference axis, and there's our radius. It's that angle. And is analogous to the linear position x. We'll demonstrate that for you in just a minute. The ordered pairs then become r and theta, and these are polar coordinates. So we have ordered pairs r, the radius, and theta. We could plot those on a graph. They're analogous to x and y. So we could also plot x and y on a graph. If we were talking about the linear motion, the object would be that far in the x direction and that far in the y direction. I could actually then take this angle and calculate y. That's the opposite side. It would be the sine of the angle times the radius. This would be the adjacent side, so I could say the cosine times the radius. So I could actually calculate x and y. You notice that x and y changes as the object goes around in a circle. So that's why we plot then the radius versus the angle. And that helps us then to identify various positions on a graph. So we say angular displacement then is going to be the change in the angle. Just like linear displacement, if I look at linear displacement is equal to x2 minus x1. In this case, the linear displacement, which we call delta theta, the change in position, the change in angular position, is theta 2 minus theta 1. Remember that delta is actually x2, d over here is x2 minus x1. Do you see the relationship here? x2 minus x1, these are position vectors. They're at a particular angle, so we measure the angle. Suppose an object moves from this point over to this point. Well, theta 1 is this angle right here. Theta 2, I would draw the position vector to the second one, and I would draw theta 2. If this is 50 degrees, and this is 150 degrees, I would simply look at that and say, well, then the change in angle is 100 degrees. Same if I were on a straight line. If my 0 point is here, and I start at this point and move to this point, this is 1 meter, this is 5 meters. How far did I travel? Oh, I traveled 4. Same here. 50 degrees, I traveled from 50-degree mark to the 150-degree mark. How far did I travel? I traveled 100 degrees. Now, I could change these then to radians. 100 degrees is approximately 2 radians, 57 degrees per radian. So I'd say, well, I'm almost 2 radians. So I can change the degrees to radians, and then we would have the the angular displacement in radians. So not real difficult to do. So we we draw our position vectors to the 2 points. We have our reference axis. The object moves from one point to the other. We have theta 1, we have theta 2, and the difference in those angles is called angular displacement. Remember that the angular displacement can be calculated. We can use, as I showed you yesterday, and as you have in your notes, you find the angular displacement using the method that we refer to as, I forgot what we call it now. You cancel things out. We want to find the radians. Suppose we're given 57.3 degrees, and we want to change this to radians. Well, we know that there are 2 pi radians for every 360 degrees. So I can reverse this. I can put the radians on the top or on the bottom. I have to figure out what I'm going to do with this. Well, I'm going to put the 360 degrees on the bottom because I want the degrees to cancel out. And I put 2 pi on the top, and that's going to give my answer then in radians. So I could use unit analysis. That's what I was trying to say a few minutes ago. This is a process of unit analysis. I cancel out the units. The other method, of course, is to use your calculator. And I couldn't remember when I came into class today. I was trying to think, did I tell you about this on the calculator? I don't remember. So if I did, okay. If I didn't, that's okay too. And if I did, we'll look at it again. To change radians and so on, we have to look at the mode. You have to decide what you're going to do. Do you want the answer in radians, or do you want the answer in degrees? If we're going to have the answer in degree, we highlight the degree sign. We hit quit to get out of there. And let's suppose I have 57.3 degrees. I want to change that to radians. Well, I have to tell the calculator what this is. Is this a, I think I said that backwards, 57.3 radians. And I want to change it to degrees. So let's just suppose I have 57.3 radians. We know that there are 2 pi radians for every one, so this has got to be about 6 times bigger than this number right here. So it's going to be a pretty big number. That'll give us an idea whether or not we have our calculator set right. But I have to tell it that this is radians and not degrees. I do that by pressing the angle button, that second function and angle right here. And I want to let it know that these are radians. So I put number 3. So 57.3 radians is equal to how many degrees? I want to change that to the degree mode. And I press in the degree number, and it's a big number. That's what I expected. And I could find this another way then. I could say 57.3 and then multiply that by 2 times pi. And I forgot to divide by 360. And that would give us our, I don't know what I did wrong there, 57.3 radians times 2 pi. Doesn't look all that bad. 6 times 57 is going to be more than, something's wrong up here then. Well, let's see what I did wrong here. 57.3, if I'm going to change radians, 57.3 radians, and I want to change that to degrees, so I'm going to multiply this by, I want the radians on the bottom now, 2 pi radians. That's why I forgot to use the 360. We had to multiply it by 360 again to come up with the correct answer. I didn't do that step right there. So the calculator gives me the correct answer, and the first answer then was correct. Let's suppose I just want to check it out to make sure that I have it set up right. Well, I know that 2 pi radians is 360 degrees. So let's put that in. Let's put 2 pi and make that radians. So I'm going to put radians in there, number 3. 2 pi radians. And what's that equal to? Well, 360 degrees. That way I can check, if you want to check your calculator and make sure it's set right, take something you know and see if it works out. 2 pi radians is 360 degrees. So 57 is going to be 3280. I could have got the same number here by multiplying this by 360. I should have added another 360 in there. Let's try changing degrees to radians. That means we need to change our mode. So we go back and we want our answer to be in radians, so I change the mode to radians. And then I quit, and I'm ready now to put the answer in radians. I know that 360 degrees is equal to how many radians? But I have to tell the calculator that this is degrees. So if I'm going to change that degrees, I'm going to go down here to angle again. And this time I'm going to put the degree sign up there, number 1. So 360 degrees, and it's going to give me that answer in radians. Well, 6.28, that's about 2 pi. Looks like we can do this problem either way. You can use unit analysis, as we did here, or you can use your calculator, whichever you're most comfortable with. I prefer the use of the calculator, as you can tell, because you're not nearly as liable to make a mistake. It does all the calculations for you. You don't forget to multiply it by one of the numbers or the others. So it's your choice as to how you want to do the multiplication, or you want to do unit analysis, or you want to use your calculator. Either way, you've got to be careful. On your calculator, the important part is making sure the mode is right. You want the answer in radians, you set your calculator on radians. You want it in degrees, you set your calculator on degree. The other thing you have to remember is that when you put the answer in, you have to either put the degree symbol or the radian. This is degrees to radians. If I have the mode set on angles, then I want to have radians to degrees. So you have to be careful with that and make sure that you have your calculator set right. The more you do it, the easier it becomes, and the more you get in the habit of setting your calculator every time. All right, angular displacement. That gave us the value. Angular displacement is related to linear displacement. Formula is a little bit different. The symbols are really the only thing that's different. In linear displacement, I would say what? D is equal to x2 minus x1. Or I could say delta x is equal to x2 minus x1. And delta x and d are the same thing. We don't have a symbol for delta theta. We don't have a separate symbol like we do here where d is displacement. That makes it a little easier in some ways because we don't have to worry about two symbols, we only have to worry about one. We have an analogy there to linear displacement that I already mentioned. The angle theta can have positive or negative values. We can go either direction. As I go back to my original drawing here, I have a circle, and this object is going to be turning. If I turn in this direction, where this is theta 1, and it goes over to this way, that's the second position, notice that my angle is getting bigger. We usually start with this as being 0 degrees, that's our x-axis, and we go counterclockwise becomes the positive direction. All the angles are positive if you go this way. The angles become negative when you go in this direction. So this is negative, and this is positive. That's fairly easy. Now, we sometimes say that counterclockwise is positive, where clockwise is negative. Counterclockwise, that's the opposite of the direction the clock moves. Clockwise is the same direction as the clock moves. So if we're going counterclockwise, it's positive. We go clockwise, it's negative. Some of you may have problems with that. I've taught my traditional class for years, and it amazes me sometimes where people have trouble with that. They say, well, clockwise and counterclockwise, I don't understand that. It's the direction the clock turns. Which way is the clock turn? And I don't know, they just get confused with that. So if you get confused with that, there's another method that you can use. We call it the right hand rule. Take your right hand. That's the one on the side. It depends on which you write with. If you write with your right hand, that's the one you write with. If you write with your left hand, it's the other hand. So, if you don't know the difference between clockwise and counterclockwise, you may have trouble with left and right too. I don't know. Most people don't have a problem with left and right. So take your right hand and put your fingers in the direction that the motion is taking place. Let's suppose that it's going counterclockwise. That's counterclockwise. Now put your hand in that direction. Most of my thumb is pointing which way? It's pointing up. We usually consider up to be what? Positive. Now if it's going counterclockwise, that's the other way. See, counterclockwise, that's hard for me to get my hand up there. Going this way. Put my fingers counterclockwise and my thumb points which way? It points down. That's negative. So you can look at it this way. If I go out from here, counterclockwise is that way. Counterclockwise, the opposite of clockwise. My right hand and my thumb is pointing which way? Pointing up. We usually consider up to be positive. Now if I put my hand so that it's counterclockwise, my thumb points down. That's negative. So the angle can be negative or positive. Depends on which way the object is traveling, which direction it's traveling in. We already talked about the formulas that you can use. You got choice of two formulas really for, this is for using the unit analysis. I would put the number of degrees here, 360 degrees. I expect that to end up being 2 pi. I could take 360, multiply by pi and divide by 180, and that would tell me how many radians. To get degrees, I put the number of radians here. 15 radians is equal to how much? Well, multiply by 180 and divide by pi. Now, if you can remember better that 2 pi is equal to 360, well, use this value instead of this value. That would be 360 degrees for every 2 pi radians. So depending on how you have to invert the formula. How do you know which one to put? Well, you're trying to get rid of the degrees. So you got 360 degrees. Degrees is on the top here, 360 over 1. So we want degrees on the bottom. Unit analysis. We want the degrees to cancel out. Over here we want what? The radians to cancel out. 360 degrees is equal to 2 pi radians. Radians cancels out here and here. So that's how you know whether to put it on the top or the bottom. And again, you can use your calculator besides that. Now, we know that we have linear speed. I know that velocity is equal to the displacement during an interval of time. Or this would be vector velocity. This would include the direction. I could also say v is equal to s divided by time. That's the distance divided by time. This would be speed. It's the absolute value of the velocity. So this would have direction to it, and this would not have direction. We have the same thing. Angular speed is going to be a scalar quantity. It has no direction to it. We're also going to talk about angular velocity. So we can have speed or velocity. Angular speed is the absolute value of the angular velocity. Same as the linear functions that we went over. It simply represents the time rate change of angular position. Now, angular speed then can be represented by an equation. We have an equation for linear. So you can add this to your little chart that we started yesterday if you kept it up, linear and angular. Well, linear speed is equal to what? The speed is equal to distance divided by time. What do we use on angular position? Well, we have a different symbol. We don't use the symbol V. Instead, we use the Greek letter omega. So that's called omega. It looks something like a W, except the tops of the arrow, the W kind of turn in a little bit more. Omega is equal to what is distance? Or in the linear, we say distance is the same as the angular displacement, and of course time is time. So that's where the formula comes from. It's the change in displacement divided by the change in time. So your notes may not have delta T on it every time. We really should have delta T on every one of those representations. We could represent it then as delta theta divided by delta T. The units then are going to be radians per second. Quite often, we do not express this as a unit. This is not a unit. I did something backwards here. It is not a unit. It's a name. We don't measure things in radians as such. It's a non-unit term. It's not a unit like meters. It's not a unit like degrees. Degrees are units. Radians are not considered to be units, and so we say that radians are dimensionless. They're a dimensionless type of thing. So if they're dimensionless, we would have the value as 1 over a second. The units are going to be 1 over seconds, or I could call that seconds to the minus 1. And quite often you'll see radians per second expressed this way, as seconds to the minus 1. If you're wondering where seconds to the minus 1 come, we went over this earlier back in chapter 2, I think it was. But seconds to the minus 1 is the same as 1 over seconds, just like if I put numbers in here. If I had 1 over 10, that'd be 1/10. That's the same as 10 to the minus 1. I bring the 10 up on the top and change the sign, 10 to the minus 1. So if I bring seconds up on the top, I bring it up as seconds to the minus 1. So this value is related to that value. So quite often they leave out the word radians because radians is not technically a unit of measure. It may be a little confusing to you, and if you want to put the word radians there, that's fine. But if you see something in a word problem that you have at the end of the chapter or homework, and you don't see the word radians there, just remember it is there. It's implied by the fact that we're using angular speed. It can also be represented by the number of revolutions per unit of time. We would call it RPM, revolutions per minute, or revolutions per second. Or sometimes instead of using the word revolution, we use the word cycle. Cycle and revolution would be the same thing. In circular motion, that's the one revolution starts at one point, goes all the way around and comes back to the same point. That is called one cycle. We use the term cycle usually with terms related to frequency. How frequent does something repeat itself? We think of a pendulum. A pendulum swings from one side to the other. It goes over and back again. So one swing from this side over to this side and back again is a cycle. It has to start at one position, go all the way through the entire process and come right back to where it was. That's called a cycle. We had a spring, and we pulled the spring down and it oscillated back and forth between two positions. When you pull the spring down to this point, it goes up and comes back down again. That's one cycle. How many cycles per second? And if we were graphing that, a circular pattern of some type, we might graph it on a chart as a sine wave. So from the top of one wave to the top of the other wave is called one cycle. So, and this is circular motion. If I put this, just took this thing and wrapped it all the way around, then you could see from this point all the way around back to this point would give me one cycle. So we use the word cycle and revolution interchangeably in dealing with revolutions. We probably more often in this country use revolutions per minute rather than cycles per second or cycles per minute. It can be clockwise, positive, or counterclockwise, negative. The right-hand rule can help you out with that. I mentioned that already. The magnitude of the instantaneous velocity that is tangent to the circular path is called tangential speed. Now, it's another kind of speed. This speed, we don't have an exact relationship to it, although we did talk about it. Remember we talked about a car going around a corner, and we said that at this point, he's traveling in this direction. At this point, he's traveling in this direction, in a different direction. And so the car is changing its direction as he goes around the corner. Notice that if you look at this corner process right here, if we were to extend it on around, this line is tangent to the surface. And so speed that is tangent to the surface is called tangential velocity. We use the symbol Vt for tangential speed. If we include the direction with it, for example, this might be 5 miles per hour, and this might be 5 miles per hour. The tangential speed does not change. It's the same. But the tangential velocity would change because the direction changes. And so we're back to the same idea that we talked about earlier in the year. We've got this object that travels around in a circle. We were talking about a highway, for example. Now we're going to talk about a complete circle instead of being on a highway. It's going to travel from one point to another point. And let's just suppose that the speed does not change. So I draw the tangential velocity. I'll call that V1. Over here, the velocity is this way, so I'll call this V2. And we're going to find the change in velocity. Does the object change in velocity? Well, it's V2 minus V1. So I have to take V2, there's V2 right there, and I have to take negative V1. This is V1, so negative V1 must point in this direction. So I'm going to take negative V1 and put that head to tail. I'm going to put negative V1 right here. This is V1, this is negative V1. So my diagonal line right here is V2 minus V1. And notice that it's going to point in this direction here. From V2 minus V1 is going to point toward the center of this circle. So that's V2 minus V1. Remember when you're subtracting, the arrow points in the different direction. So we've got V2 minus V1, the opposite. You add the opposite. It gives us a negative V1. So it's going to always be toward the center. The change in velocity is going to be, it makes sense, I think you can see. Your velocity is this way, and you change your velocity to this direction. Your velocity is turned which way? It's turned toward the center of the circle. It's always a inward change. The symbol is Vt, and we can also calculate the tangential speed a different way. Now we can see we could calculate it this way. We could calculate the change in velocity, but what we'd like to know is what is the instantaneous velocity at this point. That's a little more difficult. We can actually calculate that if we know the radius of the object and if we know the angle, the rate at which the angle is changing, or we know delta theta. We can actually calculate the tangential velocity, or the tangential speed in this case. It's by using the equation Vt is equal to r omega. So there we have angular speed. This is angular speed. See, that's what makes this a little more difficult than linear, because now On linear speed, we only had one speed. What was it? Linear. And that gave you our velocity. On angular speed, we've got several velocities. We've got the speed that the angle changes with. How fast does the angle get bigger or smaller? So that's called angular velocity, omega. We've also got an object that's traveling around the outside out here. It travels a certain distance during a period of time. Well, that velocity would be the tangential velocity, and we could say it's the distance divided by the time, arc distance. But we don't always know the arc distance and the time. We could actually come up with a formula that would show us this, but the velocity is equal to the radius times the angular speed. How fast does the angle change? What is the radius? From that, I can also calculate the tangential speed. So I've got more than one formula, again, that will calculate something. Say, well, which formula do I use? I use whichever one works. There are actually three formulas. Remember that omega is equal to the change in angular position divided by the time. So I could substitute the change in angular position divided by the time for omega. I also know that velocity is always the distance divided by the time, so for circular motion it'd be the arc distance divided by the time. Three methods of solving for a problem. Let's have a sample problem and see what we would come up with. Suppose I gave you a problem like this. An automobile moves with a tangential speed of 40 meters per second around a circular track. The track has a 300-meter diameter. What is the magnitude of the angular speed of the car? Now you've got to decide which formula am I going to use, number 1, number 2, or number 3. Which formula would be the best formula to use to solve this particular problem? Well, in order to do that, we've got to look at several things. The first thing we look at is what is the question? We're looking for angular speed. And secondly, what data do we have? I've got a 300-meter diameter. 40 meters per second is the tangential speed. Now, I have to look at the formulas and decide which formula to use. I'm going to let you decide that, and we'll ask you a pop question. And let's make it 1, 2, or 3, not for a grade, just to see how you're able to think on this. Which formula would you use to solve this problem? Number 1, number 2, or number 3? All right, let's take a look at your answers here. Those are the answers I got in. And let's look at the logic. Some of you think that the problem number 2 would be the best answer. Let's take a look at that. Well, first of all, what am I looking for? I'm looking for angular speed. What is the symbol for angular speed? Well, the symbol for angular speed is omega. So I'm going to look for a formula that has omega in it. Well, there's a symbol right there that has omega in it. I could rewrite this and say then that omega is equal to Vt over R. So I could use this formula. That looks like a formula I could use. Let's take a look at this formula. Well, that doesn't have omega in it. I could say, well, this here is equal to omega, so I could say, I could put omega in the place of this, but I don't know what the angular position is. Does it tell me what the change in the angle is? I don't even mention the angle. Does it say how many radians? Does it have time in it? I don't have either of those values in. That's not a very good equation. Let's try this one down here. Does it tell me the distance around the arc? No, it tells me the diameter, but it doesn't give me the arc distance. It looks to me like the first equation would work best. Do I know the tangential velocity? I know the diameter, and I know 40 meters per second around the track, tangential speed. It even tells me tangential speed. That's going to be 40. And what's the radius? Well, the radius is half of the diameter, so that's going to be 3,000 divided by 2, and it should be a pretty easy problem to solve. Which equation did I use? Well, I used the first equation. Why? Well, first of all, that was the only equation that had my unknown in it. What am I looking for? Angular speed. What's the symbol for angular speed? If you don't know the symbol for angular speed, you come up with the wrong choice. We'll not solve the problem. I'm not interested that you solve the problem at this point. I'm just interested that you know which formula to use. How do you decide which formula to use? Now, if an object is changing in its velocity, it's traveling around the outside edge, it's going to change its velocity. If it's changing its velocity, it must be accelerating in some way. Acceleration is a change in velocity. So if I have an object that's traveling around the outside of a circle, it's traveling this way at one time, it's traveling this way at another time, and let's say it's at constant speed. The speed might be the same, the tangential speed, Vt. 5 meters per second. Vt over here, 5 meters per second. But the velocity changed. Why did the velocity change? Because it changed directions. It was going in that direction at that point, a different direction here. So there is a change in velocity. That produces then a centripetal acceleration. Centripetal acceleration is abbreviated AC. Put a little c after it, and always points toward the center. Centripetal means toward the center. So centripetal acceleration is acceleration towards the center. It's changing its speed, and it's changing it toward the center. So think of it this way. It's traveling at this speed, at this point another one. At this one, it's constantly changing its speed. Even though the magnitude remains the same, it's still changing the direction, so it's changing its velocity. It's caused by the change in direction of the velocity vector, which is v2 minus v1. You're subtracting again. So whenever the velocity vector changes, there's going to be a change in direction. We make this a little easier this time because we find that the acceleration, your book goes through a long derivation of this. I don't have time to go through the derivation with you, but your book shows you how to derive this formula from geometry principles. The centripetal acceleration ends up being the tangential velocity squared divided by the radius. Now, we just said that the acceleration is the change in velocity divided by time. Well, you'll find that this formula right here can be rearranged so that A is equal to Vt squared divided by r. In circular motion, we're more likely to know these values than we are to know these values. This value, you already know, is pretty hard to figure out. We're talking about a change in velocity. When the velocity changes, we've got to add these vectors together. We get into subtraction, and subtraction is somewhat of a problem. So we're going to forget about this equation, and besides that, this is average acceleration, and this is going to be the instantaneous acceleration at a point. So there are two different values. If you were to solve the problem using this formula, you're not likely to come up with the same answer that you would have here, because this is average acceleration, and this is the instantaneous acceleration, the acceleration at a point. So I want to know what is the acceleration at this point because the object is traveling in that direction. Now, when you're talking about acceleration at a point, we're probably talking about calculus. But we can actually derive this equation without calculus, so that the centripetal acceleration is equal to the tangential velocity squared divided by the radius. Makes it a really simple problem to solve. So there's your formula for centripetal acceleration. And we don't have any Greek terms there, just a different formula for solving for the centripetal acceleration. We call that the magnitude of the centripetal motion quite often. It's a non-vector equation. The direction is toward the center and always opposite from r. Remember that when we're talking about motion in a circle, let me redraw that. I draw a circle. The radius vector always points outward toward the point on the circle. So the radius vector is always pointing outward. Centripetal acceleration is always inward, and therefore it's just exactly opposite of the radius vector. Acceleration is inward, the radius vector points outward. Now that doesn't mean the radius is moving. It just simply means the vector points in that direction. It's a vector quantity. And always opposite from r. So if it's vt squared divided by r, and vt, the tangential velocity, is equal to r omega, which we just had previously, that's r omega. That would be r omega squared divided by r. Well, what's r omega squared? Well, it's r omega times r omega. And divide that by r, one of the r's cancel out, and we could say then that that's r omega squared. So the centripetal acceleration also has a couple of formulas. I can use this formula, where the centripetal acceleration is the radius times the angular velocity squared, or I can say that it's equal to the tangential velocity divided by the radius. So two formulas for determining centripetal acceleration. Again, those formulas are on your reference sheet, so you don't have to memorize them. All you have to do is look at the problem as what is it asking for. The problem probably would say, okay, find the centripetal acceleration. All right, you're looking for AC. The radius is, all right, radius, I could use that formula, or I could use this formula so far. And the angular velocity is so much. I have to use this one because that's angular velocity. This is not angular velocity, and therefore I can't use that problem. So you've got to look at different equations and what they mean. From that, now you should be able to do your homework assignment. And your homework assignment is, we'll do it this way, 9-1, H 9-1, and this is due on Friday. That's tomorrow. All right, so H91 due tomorrow. We've got, what, another minute yet? Maybe we can get an extra formula in here, maybe not. Let's see, we got a couple of questions. Let's go ahead and answer these questions first. Laura from First Baptist. Go ahead, Laura.
Is it H91 or H71 since we're in Chapter 7?
Thank you, thank you, thank you. Very good. I saw a lot of hands go up. I was wondering, what did I say wrong? That's it. H71. Good girl. Make sure your facilitator gives you an extra point there for that. That was important. All right, we'll stop there then. It's a good point to stop. I've got a couple of other things left in the chapter. The next thing was to show you a video clip that we'll have to show you tomorrow. Hey, have a good day. We'll see you tomorrow.